Looking at the localized electron model and drawing Lewis dot structures, we should have seen that this does not tell the whole story about bonding. These models fall short when molecules contain unpaired electrons and do not give accurate descriptions of resonance. Therefore, we've developed a model similar to atomic orbital theories from quantum mechanics to deal with bonding called molecular orbital theory. In atomic orbitals, our atomic orbitals are solutions to the quantum mechanical treatment of atoms as wave functions. Squares of wave functions indicate probability of finding an electron in an area of space. Molecular orbitals are the same, but for molecules, where each molecular orbital can hold up to 2 electrons of opposite spin. Basically, we're taking the idea of an atomic orbital and spreading it out over a molecule to give us a molecular orbital. And we'll look at bonding in homonuclear, where we have 2 of the same atoms, and in heteronuclear, where we have 2 different atoms connected together in diatomic molecules. Now, if we start by combining hydrogen atoms together, our hydrogen atoms have s orbitals. Hydrogen A has a 1s orbital, hydrogen B has a 1s orbital. When we stick these atomic orbitals together, we spread that electron density out over this new area of space, which we call a molecular orbital. Since we started with 2 atomic orbitals, we need to end up with 2 molecular orbitals. We end up with a bonding molecular orbital and an antibonding molecular orbital. The probability along that internuclear axis gives rise to our sigma bond, which is our bonding molecular orbital. Notice that our antibonding orbital is higher in energy than our bonding orbital. These molecular orbitals, again, are just electron probability distributions. We label molecular orbitals depending on the type, either sigma or pi, the shape, S or P, and whether the electron is up or down, and then we separate them into bonding or antibonding molecular orbitals. We represent the bonding orbital by sigma. We represent the antibonding by a sigma star. The subscript 1s tells us that that sigma molecular orbital was made by the combination of 1s atomic orbitals. We could actually write a molecular orbital electron configuration for molecular hydrogen. It would be sigma 1s2. Now, if we tried to put another electron onto our hydrogen molecule, we would have to place that electron into our antibonding sigma star orbital. This would cause an unstable electron configuration. Remember, each molecular orbital can hold up to 2 electrons with opposite spin, and orbitals are conserved. So the number of molecular orbitals will equal the number of atomic orbitals used to construct them. Another thing that we have to keep in mind is bond order, where bond order is used to indicate the strength of a bond. We compare the energy of bonding electrons to that of the free element. our bond order is equal to the number of bonding electrons minus the number of antibonding electrons divided in half. A large bond order indicates a greater bond strength. For hydrogen, we would have 2 bonding electrons, no antibonding electrons. 2 minus 0 is 2, divided by 2 is 1. We would have a bond order of 1. Here we would have 2 minus 1, which is 1, divided by 2, which is a bond order of 1/2. Bond orders 1 and greater are predicted to form. Less than 1 are predicted not to form. So helium does not form a diatomic because that would require us to place 2 electrons into an antibonding orbital, which would give us no net energy gain compared to having 2 separate helium atoms. So now let's look more at bonding in our homonuclear diatomic molecules where we have 2 of the same atoms attached. Remember, we only look at valence electrons, so only valence orbitals are involved. Even though there are core shell electrons in a 1s orbital for lithium, only the electron in the 2s orbital is involved in bonding. To participate in bonding or form molecular orbitals, atomic orbitals must be able to overlap in space. For lithium, if we take our 2s atomic orbitals and combine them together, then we get a sigma 2s and a sigma star 2s orbital. We can put both of those electrons into a sigma 2s and predict that dilithium will exist. The bond order here is 1. The electron configuration would be sigma 2s2. Now boron has 3 mutually perpendicular 2p orbitals on 2 adjacent boron atoms to form B2. The orbitals can overlap as shown in B and C, and the third can overlap head-on as shown in D. The 2p orbitals in boron that overlap head-on produce 2 sigma molecular orbitals, 1 bonding and 1 antibonding. The 2p orbitals that lie parallel overlap to produce our pi molecular orbitals. Again, 1 bonding and 1 antibonding. Remember, there's 2 sets of parallel p interactions, one on the py, one on the pz axis. So we get 2 degenerate pi 2p molecular orbitals. Keep in mind that the sigma bond is stronger than the pi bond, so the sigma is lower than the pi bond in energy. So when we draw out our energy diagram for the molecular orbitals of boron, we have our sigma 2p followed by our 2 degenerate pi 2p orbitals, then our pi star, followed by our sigma star 2p orbital, molecular orbitals, for a total of 6 molecular orbitals. We also have our 2s molecular orbitals for boron, so as we begin to fill our electrons, we have 6 total electrons going into a sigma 2s, a sigma star 2s, and then a sigma 2p orbital. Now there's this idea of paramagnetic versus diamagnetic, where a paramagnetic molecule is attracted to an induced magnetic field because it has unpaired electrons, and a diamagnetic molecule is repelled by an induced magnetic field because it has no unpaired electrons. We see that boron is paramagnetic, and the previous energy diagram does not account for that. Sometimes what we see is sp mixing, which lowers the energy of a pi 2p orbital. This allows us to give unpaired electrons to the molecular orbitals of boron and account for its paramagnetic property. So we can go through and examine many of our elements on the basis of bond order and paramagnetic versus diamagnetic properties. Now let's turn our attention to heteronuclear diatomic molecules where we have different atoms connected. The previous examples had identical atoms, and so the atomic orbitals were the same. We'll start off by looking at atoms that are close together on the periodic table. Since the atoms are similar, we can assume that the atomic orbitals are similar, and we can use molecular orbital diagrams similar to what we saw for homonuclear molecules. So we could write a molecular orbital diagram for nitrogen monoxide using the same idea of conservation of atomic orbitals to give us our molecular orbitals. For the nitrogen monoxide ion and the cyanide ion, we would have identical molecular orbital energy level diagrams. Now, if we look a little bit more closely at hydrogen fluoride, which are very different atoms, we have to construct our new molecular orbital energy diagram, making a few assumptions. We'll assume only one p orbital from fluorine is involved and that the others are all localized. Here, the fluorine 2p orbital is lower in energy because fluorine binds electrons more tightly, which means it's more stable and lower in energy. Also, the fluorine 2p orbital is closer in energy to a sigma molecular orbital. Thus, the electrons prefer to be near fluorine, giving fluorine more electron density in the final molecule. If we look at an energy density map of hydrogen fluoride, we'll see much more electron distribution close to the fluorine nucleus.